Hi, Zubin. Hello.
Yeah. Hi.
Yeah, I'm not sure. I guess this is mid-sem exam week, is it?
I don't know. I just had one midsem last week. Uh, I don't know about this week. Why?
No, 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 no. Yeah, so the people
Midsem.
ask for extension in the other course, so I was wondering if how many people would show up today. How about the conducting mid-sem exams?
Uh,
Need to also
it
conduct.
was just a 2 hour exam, like a 2 hour assignment kind of thing. Like the assignment was uploaded on Moodle, and you have to submit within 2 hours. Open book.
Um, I see. Because the questions were all designed so that it was like an open book 2 hour exam, correct?
Yeah, yeah. I just had one midsem, so I don't really know how most people are doing it. This is just, and it's a data science course too. I don't think none of my other courses are doing midsems. I think SMT is not, right?
And I'm thinking of having one quiz or something like that, something similar to that.
Okay.
There will be some parts there which they will not have any assignment over. I mean, on something here also in a similar situation.
Sir, in SMT, how much marks would the assignment to carry?
Yeah, I should make that, man. I mean, I will. Yeah, by tomorrow's class, I will make the grades. Okay, I mean, I will make the
Sir,
weightage.
because I wanted it to be, if you don't mind, could you assign some more points to assignment 2? Because I found it very hard and it took me some days to do it. So
Wow.
it's like if
Okay.
it's for only for 10 marks, then I feel
Nice. Yes.
all my
Yes.
hard work is in vain. Like,
Yeah. Yeah. So maybe I'll do that. I need to revisit that anyway. I had published uh, the weightage, rough weightage, correct? So your request is to go revisit it, correct? Yes, Kapil?
sir, could you repeat?
No, 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 no. I had already published a weight distribution for the various
I think it
requirements.
was worth 10 marks or something.
Okay. Okay.
I want it to be at least like 20 marks because, sir, I have actually done a lot of work in doing this assignment.
Um,
And it was not easy actually. I had to do a lot of experimentation and debugging.
So let me discuss with Madhukar. So it's 3:35 almost. Why don't you guys unmute your thing? I want to see how many of you have done what I had asked you to do. That is, implemented AX and EX in terms of DDDs. Have you guys
Sir, I have done.
had a start? Okay.
Yeah, I have as well.
Like, I tried, but there was like some error and stuff, and I couldn't fix it really.
This is Rishikesh. Huh? Okay. I wonder what we should do today, since we have very thinner than usual crowd. My goal was to discuss the other aspect of the thing one at a time, or move on to a new thing. I mean, Kapil, you had, let me share the screen and see what I.
So will we be getting test cases for our assignment?
That's a good this thing. I think, yeah, we will.
Sir, I think doing a fully working model checker will be very hard because we don't have any parser for it. Like
Correct.
we can show the working of our model checker for some given test cases, but it's not like that we can
Yeah.
model checker where you input the test cases, input the formula, input the transition relation, and it gives you this thing because you don't have parser, right?
Yeah. What do you think, Zubin? I think I'm okay with that.
Yeah, so we
an
can,
alternative. Yeah, go ahead. You had some suggestions.
or we can give you a parser and a skeleton for the model checker.
A parser, will you be able to give it in Python?
Yeah, Python will. Everyone's using Python here.
No, I have done it in C++. Sorry.
Okay, so
That's why I was suggesting that there will be some test cases, and we will show the working of our
in Python you're using the DD library, right?
yeah, DD. I'm using DD.
Yeah, so DD has a parser for Boolean formulas already, right?
No, I'm not referring to formulas. I'm Boolean formula. I'm referring to SMT leaf formulas. Not SMT leaf formula, the CTL formula.
Yeah, so
So we need a parser for CTL formula too, right? And then also we need.
if it's just Python and C++, then I can write parsers in both of those for you.
We will also need to encode the transition relation, right? We'll need.
No, but you can use the parser. It's the transition relation and the atomic predicates.
Those are just
those are the real ones. After that, all for the particular CTL formulas, that is easy to just do it in the thing. You don't need a parser for that. I mean, even if you that is so you can do that hard coded.
We need to do these things. We need to first declare the variables to begin with. So we must first know what variables are there.
You just need to know the number of variables, right?
Okay, yeah, number of variables. No, not exactly, because in the formula it will be something. If it's something like
no, so you can require the formula to be of the form x0 to xn, y1 to yn.
Yeah, we can require for that. Okay, so first of all, we need the number of variables. Then we somehow need to make the transition function. Means okay, at least
the transition function is a simple Boolean formula. You can use the parser that's built into DD for that.
Okay. Yeah. But I thought that the syntax in which Boolean formula is represented in DD in Python, it will be different from C++, right?
Yeah,
So it,
probably. But
Yeah.
it's like same input uh, will not work for both the languages. We will need to have different input for different languages.
So is there any like, are we specifying any specific syntax for our formulas that the parser would have to
Yeah,
adhere to?
exactly.
Like, or like, as in, do we have to write an SMT-lib like parser or
No, I don't. No, I'm not particular about that. You can choose whatever is convenient for you, as long as you can you can test your own stuff,
Okay, sir.
and
So
we'll give a set of formulas for you to test and give the outputs on. So those things you can use your own syntax. So
okay.
Right.
I think
so
that
you can
will
use
be
your
good.
own syntax,
I think
and
that will be good, sir.
yeah, and we'll give you the formulas and you translate them yourself and show your translations in your
Okay, yeah,
syntax.
that we can do.
So then, because you already have parsing for atomic formulas, then you just need to mark formulas with the CTL operator and then recursively somehow.
In fact, like, I think I like checked a few days back. There are some like gists where you have like a list like parser given for C++, and I think Python also. So we can just modify
Yeah.
one of those, and that can be a very good starting point.
Yeah. So if you just look for S expression parser, then you'll get a ton of those.
S expression.
Yeah.
So I was going to ask you one question. Rishikesh, did you, Rishikesh, if you could unmute your mic. Do you have any issues these people seem to have? I'll ask some specific questions about your implementation as well. But are you having any issues, or are you okay that you want to discuss and ask about? Rishikesh, are you there?
Yeah,
Yeah, my question was, if you're having, since you said that you still have not completed it, are you having any technical issues that you might want to bring up, or not yet? Huh?
I don't know. I just like find the coding kind of.
So what language are you planning to implement it in? Python? What language interface are you going to be choosing? Question to Rishikesh.
Yeah, I plan to use Python.
Yeah. One question I had in your implementation, both Kapil and Diganta, how did you do when you eliminate a set of variables used in existential quantification? And if you want to do repeated EX, or for that matter tau, if your eventual goal is to define tau and then iterate over tau, since tau usually will have an existential quantification elimination as part of the logical connectives. When you do it, what you will get is, because the formula will contain T, the binary relation TSS prime and some predicate over S prime or S. So what you end up getting will be a variable on over S. But the next time you want to apply, you will, your TSS to TSS prime the variables will have to be flipped. How did you get around that problem? Because when you want to do EX of EX or something like that, so after the first application of EX or AX, you get a BDD which will have, if you started with TSS prime, it will have the variables S. The next time, if you want to use the BDD for the same BDD for the transition relation, that will be TSS prime. I don't know if you try to do repeated EXs or not.
Yeah. So I tried something like this. So the current thing that I'm basically thought about working around this issue is instead of instead of defining this T as a BDD in itself, we define it as a function that takes in two variables and gives you a BDD, suppose. And then when we're iterating, we're basically instantiating like several different BDDs, copies of the same BDDs using different variables, and then combining.
That is one approach. Okay. On the other, there is something called swap variables. Okay. There is a function called swap variables as a utility, a BDD utility. So you could swap the S once you do once EX once, you will get the BDD in terms of S. Then you could change those variables to S prime and then use it. In the BDD, you change it. Or you keep, I'm just giving the alternatives. I think what you suggested was maybe the more elegant solution, but this is also can be used. Or you can keep two versions of T, one as SS prime, and the other one is TS prime S. And then you can flip. I don't think I like that solution very much. Or you could swap, or you can define. So Kapil, you said that you had implemented it. Did you think about this issue? This occurs only when you want to do repeated tau application, which you will do, okay, when you compute fixed points. So that's why I'm asking this. Kapil, do you understand the issue? Rishikesh, do you understand the issue?
Sorry, sir. I was talking, but my mic was not on.
Okay.
Okay,
Yeah.
so what I did was I did not compute the BDD right away. Let it remain as a formula only. And then I applied EX again on that same formula. And after all formulas are done, I computed the BDD.
Oh, no. Yeah.
Formula, you mean function or what?
Yeah, means the formula which we get after applying EX.
No, but how are you doing that? By EX of, say,
after EX of P, we get a formula, right?
No, I understand that, but how do you do EX itself?
EX, I did the existential quantifier.
How?
That
How
is,
do you?
that is clear, right? I replaced the free variables with S prime and then just substituted to get that.
So you do no.
When
you have to quantify logically, what it means is you have to replace the variable that you're quantifying out with 1 as well as 0, then take an OR of that. Is that what you're doing?
Yes, sir. The formula,
no, that is not good. See, because if you
lets you replace the variables, sir.
Huh?
DD library lets you replace the variables. Hello?
Yeah. DD library lets you replace the variable only on variables inside the BDD, but you say you're not even constructing the BDD. What does that mean?
No, means replacing the variable in the
Can you show your code? See, because if you're not constructing the BDD and the existential quantification elimination is not being done on BDD, your formulas will explode, okay?
No, sir. Actually, what happens is when we do BDD add expression, it does the means it parses the it makes a BDD out of the formula, and the formula gets gets in a compact form, and that it returns.
Yeah, so it means it is constructing the BDD and the
It's constructing
existential.
the BDD internally, and it returns the formula. Means after
That is okay, but still you're keeping it in the BDD. Everything is only in BDD. I don't know what you mean by you're making a formula out of it. The existential quantification elimination.
my code.
No, do you understand, Zubin? I mean, I certainly
Understand
don't.
what you're asking. I just don't know how to
Not really.
describe
Can
it.
you show
because
your
I
code?
don't-
Can you show your code? I will make you a co-host.
Yeah, I can show my code. So can you see my screen?
Not yet. Yeah, now I do.
Okay, sir. See, what is this is an expression on which we want to apply EX. This is like a formula, but it is the formula which you get when you do this. BDD.act expression something. It's an object. It's not
Yeah,
exactly.
but that is BDD.
This is the BDD.
No.
Yeah.
That's the BDD.
BDD writes in the BDD variable, but what it returns is what we want.
Yeah, but that is BDD.
It returns a node in the BDD.
It returns a node, which is actually the BDD.
Yes, I don't know actually what internal workings are there, but it's
No. You don't need to understand the internal working. All you need to know is what it returns is a BDD. Okay. And then when you do anything to it, you will have to do some.
Okay, I think it returns a BDD, but you can treat it like a formula.
No. But BDD is a formula.
Okay. That's thing. That's the same. Yeah, same. So what we get it? This is a BDD, which you can also refer to as a formula, right?
Yeah, that is fine. So EXP, but what you're passing, where are you calling EX? So yeah. See, you are doing BDD. Where are you creating? Okay, let's look at EX of EXP.
Okay, this thing. Okay, so we instantiate the BDD and declare the variable.
Mm-hmm.
Okay, then what we do is PX will give you this BDD.
Mm-hmm.
Okay, then we apply EX on it. We'll get another BDD. Then we apply EXP another BDD, and then we apply equivalent sign to these two. We get another BDD.
Yeah, but let's look at the EX definition. So that's fine.
Okay.
But the EX definition,
EX
when you eliminate the existentially quantified variable, see if you do exist S prime, EXP S prime T SS prime, the result will be BDD over S. Okay.
Yeah, it will be over S.
But the next time you do EX,
it will be over S only.
Huh?
It will be over S only.
But TSS prime is expressed as SS prime. So.
But he's parameterizing trans with the free variables, right?
Where? Okay, that's what. Where is the
third one? The third line. The third function. Fifth line.
Oh, so he is.
Fifth line is there, yeah.
So he's flipping the variable, correct?
Yeah.
Okay, so that's what I asked. So you are flipping the variable. So you're constructing to do a trans of star free prime. So those are passed. Just like he's doing pretty much what you're doing, correct, Zubin?
Yeah.
Yeah, but the only thing I'm concerned here is that, but trans is constructing a BDD as long as you, so since it is, then he'll be constructing T S prime S here. Correct?
Yes.
The second time you will be constructing T S prime S and then you'll be applying.
So what happens is S remains as a free variable. So what I'm taking is I am taking the free variables, I'm creating another prime variable and then replacing them by replacing S by S prime. So you get X S prime. Okay, sir?
Yeah, you get So you're replacing s by s prime. That's what I meant. Okay.
Okay,
So you will have to rename the variable.
so
So
this
you're
function lets you do that.
yeah. So that's what I asked you. So so you are actually replacing the variable in the BDD before you apply it again. Okay. So that's fine, because that's what you will you will need to do. Okay. So this is also fine. Yeah. Um,
I can show how to do it with renaming.
But
in Python.
with renaming means, yeah, so show your code, okay? So people will know, and we can actually put that code up.
Can you
Let's
make me a
stop.
co-host? Yeah.
Yeah, I will do that.
Okay, this is visible, right?
Yeah.
So yeah. So EX is very similar to what Kapil did, but instead of parameterizing trans, we just construct trans as a relation between xi and yi. So we have some number of xi's, some number of yi's, and trans is a relation between xi and yi. So in this one we just set y1 to false and x0 to x1. Uh, so um, in ex takes the number of variables, the transition relation, and the atomic formula. And what we do is uh, look at we construct we first take the uh, we do existential quantification over all the yi's, uh, and so trans is over x naught y naught and we assume that p is over y naught so when we existentially quantify over y naught uh, over the y's, then we uh, get a formula quantified over x's. But when we want to say, so this is applying ex once, but when we want to apply ex twice, um, given this transition relation, and again two variables, what we want to do is uh, so ex expects a formula over y naught. So in the end, before we return, we rewrite the formula to operate over the yi's instead of the xi's. So this line does that, and we can run it, and we can see okay, if we so our transition relation sets y1 to false and y0 to x1. So in two runs we would always be false, right? So both x0 and x1 and y0 will be false. So to verify that, we can give a proposition like uh, y0 is not equal to y1, and then look for models of that, and we see there are no models of that, so it's unsatisfiable. So yeah, this is how to do it without parameterizing trans or and so we only construct the BDD for trans once. Uh, it's rewritten over here, but there's only one BDD here, so we don't have parameters for each time we do an EX. Uh, any questions about this?
Yeah. But this is not the okay. This is one way. I mean, you
Yeah.
also want to show the other way. So, did any questions? Yeah. So here you're not even. Where are you renaming here?
So this let is the renaming. So we rename all the.
That's what here also used.
So we yeah. So we rename all the YIs to
Correct.
Xis to Ys.
This is
So-
one way of doing it. Yeah.
Yeah.
We also had
Yeah. So
done it another way. So is that clear? Okay. So although there is, yeah, Rishikesh, I mean, this code you can have done code also. So yeah, so he's going to be showing, this is pretty much the way that Kapil has done.
yeah, this one, but except we're not parameterizing trans here. So trans is
Parameterizing trans, correct.
so trans always over x naught and y, x and y or whatever. So we don't ever construct multiple versions of trans, though that is what
Yeah,
let will be
but-
doing.
Because it's passing
Then-
trans as an argument, right?
Yeah, we can also not pass it, right? Because if you want, so ex is parameterized over trans over here, but we can just do this and it'll be the same.
Yeah, but then I think the variables that trans uses kind of hard coded in here, and the assumption here is that ex will assume that those are the variables. Okay, so that is one issue. So but so if the input trans that you're going to be supplying uses a different set of variables, then you won't. Then you'll be in trouble here.
Yeah,
Correct.
yeah,
Sir,
Making it a parameter will help you there.
yeah,
Just kind of what Kapil had done. So he had made it a parameter, correct?
yeah, yeah.
sir, that's why I was suggesting this. Consider this is only a feedback, okay, sir.
Uh-huh.
That actually doing model checking with only this stuff is already hard enough, sir. Means generating counterexample will be even harder.
You already on
That's
EX.
why I don't want it to be a
How?
part of assignment.
Implement how? It's just one more while loop on top of that. That's it.
No, sir, no, sir. We have to worry about a lot of other things, sir. So like, we need to, because see in that formula, sir, it's something like F1 and F2 or EXZ, right?
Mhm.
For the formula of F1U F2. So here we have to make Z as a formula, right? Not a set of states. We'll have some issues there, sir. Because in the explanation given in the book, EXZ is supposed to return a set of states, right?
I'll explain it to you now. So there's nothing at all. Okay. So if you so let me see.
A set of states is a proposition on
The
states, right?
proposition is just everything is a formula. That's it.
Yeah, then we have to convert that into a formula and do stuff.
So it will be a formula. When you compute it, it'll be a formula. Like
No. Just for he has used the set of states just for convenience to
as a conceptual thing, but
as a
it's
conceptual thing. Everything is only formulas. Okay, so computing fixed point, you can have that while loop half a day of work. Okay, and
It's not half day of it will take 2 days, I think. Sir, it is actually difficult, sir.
no, I think you are overstating that. Okay, so
No, sir, doing this EX only took me like some 2-3 hours.
that's what I said. Half a day is half a day is 6 hours. Okay, so implementing a CTL operator is half a day's of work. Okay. After that, so I'm even going to give you describe. I was planning to spend. I'm planning to spend today to describe to you what the thing is. I don't think that will be that difficult. Okay, you can forget about all the extra advanced options. I certainly want you to do the checking under fairness. Okay, and the counterexample generation, okay, which I will describe, and you'll figure, we'll see how difficult it is. Okay, so you want to show the I guess since there are not very many people here, you can show it for completeness, then let me take the rest of the class to show what it means to implement the complete model checker and the fairness, as well as counterexample generation. Okay.
Okay. So this is the parameterized approach in Haskell, where you take a transition relation between A and B. A and B can be any number of variables. It can be one variable, it can be two variable. So A and B are always of the form DD node, are all tuples of DD nodes. So this is, so if A is equal to this, then that means the transition relation takes two variables as input and two variables as output. If it has three elements, then it takes three variables as input, three variables as output. A and B are usually the same, but over here we make them different just for clarity and because the type checker can help us. Will complain if we mix them up. So a relation is between A's and B's, and EX takes a predicate on the output and returns a predicate on the input. So the way this is implemented it is some A belongs to the input if there exists a B such that PB and R of AB. Yeah. So
That's lambda. Slash is lambda.
yeah, slash is lambda. So we are saying A belongs to the input set if there is a B such that PB and RAB. So we can use it with the one variable thing. So if we have a transition, that this is the first transition I showed you, which was PSM. The output is simply the not of the input. XOR, it's implemented using XOR, but say we want to get all satisfying instances of EX trans of the proposition we're giving it is the output is equal to V2 given the input V1. So we'll get all possible runs, which is
In
0,
general, I
1.
mean, I know that you are doing all SAT using all SAT.
Yeah.
Okay. But I mean, a more general way of doing it is you define what the expected function is
Yeah.
as another predicate. Okay. And then do
So here we can give any property like
Yeah.
V2, sorry, slash A, A
yeah.
false, and false you have to define some false equals P naught read 1. Read 1 is true in Haskell, so something like that. But and we can also apply it twice. So if you apply it twice, we get all runs in two steps, which is 0, 0, 1, 1. And then this also generalizes to transitions with multiple variables. So if you have a transition between two variables, then you can do the same thing, getting all runs of length 1. So this transition is D equals false. And so no, it was this. I had just changed that for debugging, but the transition
Most
was
important thing. I mean, just
flipping the bits.
things,
Yeah.
okay. He is parameterizing the
Yeah.
trans with respect to the variables.
Yeah.
That's
So over here, trans was parameterized. So this was similar to what Kapil had done.
So this is what you had in mind, Diganta?
Yeah, this is exactly what I mean.
Yeah, but doing this thing in C is a little bit. I guess you can do it in C also.
In C++, C++ has higher order functions. Are you using them? Or,
Yeah.
yeah. Okay. So I'll leave it here.
Yeah, okay. So let me share my screen.
Sir, can we see Diganta's implementation? I wanted to.
Yeah, you want to see it again here? He'll upload the code. Do you want to see it on phone?
Diganta.
Huh?
Diganta's code.
Oh, Diganta scroll. Okay, Diganta. Yeah, let me.
Okay.
You can share it. I think you've been made a co-host.
Yeah, is it visible? Hello?
I think something
Hello?
is
It
visible there,
is, yes.
Oh,
but it is blank screen. Yeah, no. Yeah, your
right.
screensaver is visible.
Right. So, right. So basically, uh, okay, so this is basically the main function which is doing what Sir had asked us to do. So there are, so I have actually written like a BDD class here, which will take care of a few things for us, which is essentially the manager and the reference counting and all of that things. Those are taken care of over here. So what is like the where I have basically used the fact that like I'm representing everything as objects as basically things that take variables and then give me BDD. So P and Q are basically things that take variables and then return some BDD. So this returns basically not like the BDD which will just have a single variable, whatever variable is put in here. Similarly, Q just returns not of whatever P of whatever variable is put. So if we, okay, is this zoom all right, or should I increase or decrease?
Yeah, just a little bit increasing will help me.
Right. Okay.
Yeah,
Is this okay?
yeah, fine.
Yeah. Right. So, yeah. So basically, if we do P of 0 over here, then P of 0 is we are calling this function, and this function takes like the variable 0 and returns whatever the BDD P will be for 0. Similarly, we can do Q of 0. And then over here, I have defined like the simple single variable transition relation, like the one that just flips the variable over here. So this takes in two variables and gives me the BDD representing the transition relation between those two variables. So it just XORs those two variables, like generates two BDDs for the two variables and then XORs them. And so, okay, over here now we are doing the EX of P. This is underscore V0 because this is instantiated for the 0th variable. So in general here, I have not defined an EX function yet, but like it can be done in the way that like it will take in, say, some function object that does this sort of a transformation and then return a function object that gives you something like this. So that can be done, but in like over here, what I'm doing is basically doing trans of 0 and 1 and P of 1 and then existential of that over 1. So this will basically be EX of P over 0. And similarly, we can do over 0. So if you're going to do it twice over here, then we'll have to do something like for the first one, we are using 0 and 1.
What is the 0 and 1 there?
So the 0 and 1, the variable numbers for which we're
The variable numbers. Yeah, yeah,
yeah.
okay. Yeah, yeah.
So yeah, we're basically instantiating the trans relation for 0 and 1. Okay. So it is trans of 0, 1, basically.
Mhm.
And P of 1 and then existential over 1. So similarly over here, what we're doing is trans of 0, 1, P of 1, and then universal over 1. And then here I'm doing twice. So I just, yes, this is basically 2 times EX over P instantiated over 0. So that is trans 0, 1. And then this entire thing where I'm doing trans 1 and 2, P2, and then existential over 2.
Yeah, but I think what you're doing is you're unnecessarily creating new variables, okay? You could just manage with just two if you want to do, right? because you're making trans 1, 2, trans 0, 1, trans 1, 2, trans 2, 3, trans 3, 4, and so on. That is unnecessary, because when you do that, you will be creating as many instances of that BDD, because the trans 0, 1, trans 1, 2, and if you're doing once again EX, it will be trans 2, 3. That you should avoid.
Yeah,
Because
but is that not also happening internally in
No.
no?
that's what by renaming,
Right.
because there when you rename, you're renaming in the result of the EX, the first EX, but trans you're keeping it just like that. Okay.
Right, but then in the thing where we so in Zubin's the second code he showed was, so there we had like something which took basically,
No,
so
but
there we
even
also had some
Zubin's method, maybe Zubin
right.
can show again, because there you could then use trans with the appropriate variables. I don't know why you ended up doing 0, 1, 1, 2, 2, 2, 3, and so on. The next time, since you know that the result of EX is in terms of 0, you could just use trans 1, 0 and then do it, no?
No, but then I don't understand. Like we'll have to. So if you want to do trans 1, 0, but then trans 1, 0 will represent like some transition between whatever state represented by variable 1 to 0, right? And then
Yeah.
when we nest the second EX in, we'll have to use something like trans 0 and then something else,
No,
right?
no, why? Why will the trans change? No. The trans,
No.
only the variables will have to change. Okay. So either you change the variable of the result of the first nested application of EX. When you eliminate variable 1, your nested EX will be
Right.
in terms of variable 0. The next time you apply, what you will need is, if you keep the variable in the result of EX as 0, you will be
Yeah, then we can
can't
do
use
trans 1, 0. Yes.
you
Yes.
can't use trans 0, 1.
Yeah, we can use trans 1, 0. Then what we will get would be a BDD in terms of 1, right?
Yeah, but that's what. So you could keep flipping that. You could use trans 1,
Yeah.
0.
Yeah. You're right. You're right.
Keep
You're
flipping.
yeah.
Change the variable.
Yeah, we don't have to do that. Yes, that is true. Yeah, we can keep
So
flipping.
here you will be creating so many.
Yeah, that did. Yeah. That is a very yeah.
No, that is the most important thing that I wanted to avoid. I mean, I'm belaboring this thing, okay? Because then the whole object of using BDDs is completely gone, okay?
Right. Yeah. So
So
yeah, essentially,
either, that's the most important thing. So here, although you're using variables as parameters, you are not exactly exploiting. Zubin, you have to make yell at this point, okay? Because she said something about your code, which is not true.
no, I was just like I just got confused as to.
You guys understand this? I don't know. I mean, you say. I mean, I think this is a subtle point. But Zubin, are you there? I don't know. Maybe he is.
No, yeah, but I do understand. Like I was thinking, I don't know why. Yeah, it didn't occur to me the fact that we can just keep switching variables. So this is basically would be what.
Or you do what Kapil did. Okay.
Yeah.
You could rename the variable in the thing. And I wanted to know. I mean, I wanted Zubin. Oh, he's gone.
I think you would have problems making a formula something like EX with an EX of a formula, so arbitrary formula. I think you'll have trouble doing that, right? Because here you are using just variable, EX of a variable.
No. Yeah, I don't think that will be like over here. We are doing say. So, are you asking how you want? How do you create like a
Is
method which
here
takes some
EX0, what you did was trans 01 and P
right,
of 1, right?
right,
So if say instead of P there was something else, some other formula, then what you would have done?
I mean, I would have used whatever is there. So are you asking, like, say, so basically, are you asking me to write something like this? Some uh, ex, sorry,
X
some
of P and Q, something like that.
right. So something like some ex method which takes some type and then some for arbitrary formula here. And how would you do this? Is that
Yeah, exactly.
right? So basically, what I plan for that is something along this line. As in, I'll basically I'll define these formulas, these p zeros and p ones as function objects. Say I'll have some class uh, f, let's say, and then I'll do something like this basically. So and then over here this will take in, say, variables int v and whatever, and then here this will do whatever to give me the proper BDD. So this will be the definition of whatever arbitrary formula I have. This can have, some constructor which parses, so I can have some constructor like this which takes in a string and then parses this and whatever. So this will give me the BDDs for instantiation of whatever formula is I pass in over here. Now I can do a EX which takes something of type F and then returns, say, BDD given say type F, and then whatever variables I want. So I give an FF, and then whatever variables I want the final BDD to be instantiated in. So this I can do. There I'll just do something like return, say, basically trans v0 v1 and then
Okay, I think Zubin is back. So you could. So Zubin, are you back?
Yeah.
Yeah. See, what the important thing was what he was doing. Was, right now he was exactly, was doing one that I wanted people to avoid, which was creating a new version of trans every time.
Okay. Yeah. With new variables, right?
Yeah, with
yeah,
variables, and then you will end up.
Okay, so the way I avoid that is I look for the free variables in the or the
I was intending to do the same, the taking free variable.
not the free
Sometimes-
variable, like the complement of the free variable, whatever variables aren't used, and then I use those to existentially quantify.
Yeah, but sometimes what will happen is the BDD, if even if some formula is something like that, there exists X or Y. There exists X such that X or Y is true. Then BDD will interpret this formula as true, right?
Yeah.
So we have actually Y is a free variable here. But if you make this formula into a BDD and check for free variables, it will return nothing.
That doesn't matter because as long as that can be reduced, you don't need to quantify over that.
Okay, yeah, all right.
Okay. So any
non-free variables are from using something like that.
your voice
Right.
got garbled.
Hello.
Yeah, now you have to repeat.
Hello.
Was
Hello.
येन
Hello.
स्टंप से बाहर जा रही थी, फिर भी रोहित
Hello.
yeah, we
Hello.
can hear you.
Okay. I don't know what happens. I think yeah. So basically so over here, for example, since the state is represented by just one variable, we can just, I can see how one can switch between those two variables easily. So in general, will we just have say some set of variables v1 to
Why
vn?
is that
Yeah,
different?
so if you
Yeah.
That whole set of variables, that's all.
Yeah. So that is all right. So
or if you're using integers as variables, you can switch between even and odd variables or something like that.
yeah, right. Basically. Yeah, okay, fine. So this is fine. So uh, should I stop sharing or?
Yeah, please. Yes. Okay. So, I will. Yes, I will share my screen. I want to show. Yeah, I'm going to show what is involved. I mean, I'll go in this order. P1. Okay. Yeah, now I think it's clear now. So what was the decision on parsing? Okay, you could do, there is no SMT lib or anything. You can choose whatever, as long as you read in whatever input syntax notation that you are comfortable with. It is fine with me. Okay. So we have solved this parser issue, correct? Any questions about that? No? Well, I'll take it as there's no question there. Okay. So in order to do your thing, you've already done EX. Okay. So you're able to see my screen, correct?
Yeah.
So if you've implemented EX and AX, then you will just define a tau. You already know. I mean, Z is just a formula here. And you construct this BDD and you do this, okay? The only thing you have to take care of here is when you do a tau, you start, once you define a tau, you just have to implement this, these two things. This least fixed point and the thing. So how much time will it take? Okay, you have all the infrastructure already done. So yes, what you will have is each time, you'll start with false. The next time it will be FS. Okay, so you need to be mindful of the variable change that you get. Each time you'll be getting the a BDD in a different one. As long as you're taking care of it, and you have already implemented, you're just iterating over a different thing. So how, this is all the thing is, and you have, these two things is all you have to implement. Okay, that is one. For each CTL operator, you will have to do this. Okay, I mean, for each, you will have one code that iterates through a given tau. Okay. And I mean, the same thing you will be using either as greatest fixed point computation or least fixed point. It is just the tau that you will have different things. Okay. So any questions here? But when you do it for a CTL operator, okay, let me get, yes, you will have one more layer, okay? So each of these things, okay, although I've shown it like this, you can have a procedure called check AF, check EF, check EG, AG, EG, and so on, okay? And you'll be either, yeah, and the code will be just the while loop, okay? Now, but of course, that you will have to have one other loop above it, because this can be nested. So you will implement check given, you will implement check AF, check EF, check AG, etc. as a parameter with respect to, that will take as a parameter a formula. And in the case of U, it will take two formulas, okay? And it will compute the fixed point on that. And then return the formula using those two loop code. After that, in order to do model check CTL, given any formula, what it will do is it'll iterate over the operators. Okay, it'll start bottom up. Okay, so and it'll iterate over the CTL operators as big as as many times. So that's another while loop. Is that clear? Hello?
So essentially, we'll be doing some sort of induction over the CTL formula itself.
There is no induction. What do you mean by induction?
Sorry. So we'll basically compute the the final fixed points for the two sub-formulae and then use those to compute the fixed point for that.
Yeah, so
Yeah.
you will exactly implement this thing. Okay, it will just be this loop. This one loop implements the, the tau will be different, okay? I mean, you can even make the tau as a parameter of the thing. So it will start with false. Once you define this is a BDD. It takes a BDD and constructs a BDD like this, okay? And AX itself will eliminate the quantifier. So suppose Z had, to begin with, this will be false, okay? You will actually instantiate this with false, okay? To start with, and then you get a BDD which will be in terms of some set of variables, because AX will have will be defined in terms of it'll have a universal a quantifying elimination, and F1 will be just a predicate on some set of variables. The whole thing will be if the transition system is S0 S1, S1 will be eliminated. F1 will be, function of BDD, a function of S0, S1. So you will get a BDD which is over S0, okay? Now, there you will have to now rename that variable, because the next time you will be passing that, okay? That's exactly what you'll be doing. You'll be repeatedly applying tau here, okay, on the result of the thing. So you are, each time you're creating a new BDD, and there is a check that you will have to do, to see if they are, equal or not. So you will be keeping two BDDs, one, the previous one, and the one new one, before you do the check to see if you have reached the fixed point. Otherwise, you will just keep applying tau. Now, it's only that variable renaming will have to be done, okay, in between the applications, because there will be existential quantification elimination. So that part of repeated application you will have to do. Otherwise, you'll be repeating this for a particular tau. Now, you will have to decide, whether it is for each operator, what you'll have to, whether you have to do it, use GFP or LFP, okay? Depending upon the thing, that's it. So computing the fixed point means defining the tau in terms of the parameter, and when you apply them, each time you have to do the appropriate renaming, okay? To do the check. I mean, before you apply the tau, you will have to do, so which you will have to do anyway, because what you have Q and then you compute Q prime, and those two, you will have to make sure that they are over the same variables before you check them, okay? That they are equivalent. If they're equivalent, you stop. If not, you will apply tau once more. And you will define your tau as per these things. So whatever is in the right-hand side here. Now, for an arbitrary CTL formula, it will be a loop about this, okay? Where you will, each time you recurse down. Maybe that's what you meant, Diganta, when you said recurse down. Yeah. So you will have to start from the bottom, in the innermost CTL operator, use whatever the check on that will give another BDD, and then you keep on, keep on doing it. That's it. Is that clear, Kapil?
Yes.
So do you really think that once you implement these things, all of them just get either instantiation of either GFP or LFP? That's it.
I don't think this will not be very easy, at least. It will.
Well, that depends on what you mean by easy, okay? It's not like, if you do one, it's just almost one of LFP and one of GFP, it's cut and paste, isn't it?
Yeah, but still.
Okay. So let me do view here. Yeah, I know coding is not always. So see, the fairness to do EF, G of F under the assumption of fairness. Okay, it's a nested a fixed point here, okay? So here, what you will need is that, because, see, what does it say? It has EF inside EX, okay? So what this will require is, in each iteration of a GFP, okay, so here, so let me make this is, yeah, in each iteration, besides applying, in order to apply this tau, you will have to now, there is a nested fixed point, okay, that you will have to compute EF of U of this. For each Q prime that you get, you will have to compute this, okay? That will mean that you already implemented EF, EU, so, you will have to call that procedure EU on this parameter, okay, on the latest one that you get. What Z here is that after applying it, in order to apply this tau, what you will have to do is you will have to compute another BDD, which itself is a EU. You've already implemented EU. Into that, you will take whatever is the current BDD in this while loop is, and you check that, and you will compute this, the fixed point. I mean, once again, you will get the BDD by invoking for EU, which you've already implemented. So what will happen is in each iteration you'll be in the process of computing tau will involve an invocation to a EU operator itself. Okay, that is what you will you will have. Okay. And are you with me, or you have any questions? So this will involve a nested fixed point computation. Okay, in the sense, in each iteration of this fixed point computation, you will have an invocation to on the partially computed partial fixed point, okay, that you computed. You will have to invoke a EU, okay. After that, what you get will be just the usual routine EX, okay, and then you have to take the conjunction and so on. Yeah. Any questions? Kapil, you are the one who is usually not shy of asking questions. You think it's hard?
Sir, that I can only tell after doing non-fairness CTL checking first.
Okay, so let's do. So yeah, and then now let me get to yeah. So this is, yes, in each of the, here after every tau you will have a partial result. You will have to invoke in constructing that you will have to in turn invoke EU. Okay, that's all. That's what you will have to do, and you will have to think about that. Okay, so and so that will be a bit of a modification of this basic code. Okay, because you will, and that also will be just an invocation. If you've already implemented check EU, or which the computation for EU, the BDD, the procedure that computes the BDD, the fixed point for EU, all you have to do is one extra invocation there, and then you get the BDD, and then you do the rest of the thing that you'll have to do to get the tau. That's all. So that's that is what is happening. Okay. Now, so let me get to describing what is involved in generating the counter example. See, as I said, generation of the counter example, I don't want you to do it in the presence of fairness, okay? Just for the basic part of it. So what is a counterexample? So for a universal operator, AG of F, a witness to not of AG of F. So witness to not of AG of F from an initial state. So not of AG of S is EF of not of F. So you have to really make a witness to EF of not of F. So which means after you run AG of F, if it becomes false, then what you have to do is you have to produce a witness to EF of not of F from. So what you already have a state which is violating AG of F. What you will have to generate is a path from that state to the point where you will have not of F. Okay. Now, that's what you will have to do. How about for an existential operator? The counterexample or the witness is defined as whatever that it makes it true. Okay. So in both cases, anyway, so generation of a counterexample is reduced to the problem of showing a witness to an existentially quantified thing, because a witness, when you're verifying, checking EF, all it requires you to do is generation of a counterexample is not when it is not of that, but rather if it is true in this, for a universally quantified thing, if it is false, then you generate a witness to the negation of that, which will be an existentially quantified operator. In the case of if the formula that you're starting out with is an existentially quantified thing, then if it becomes true, then you will have to generate a witness to it. So in either case, what you have to do is to generate a witness for EF, EG. That's an EF or EU and EG and so on. So it's the same thing here as well. So how would you generate that? Okay, so what you will have to do basically is to go back to this thing. Okay. So if you're doing this LFP, so let's look at that. Let's suppose that you're doing this for AF1 union F2, I mean UF2. So what you have to do is you save the BDD in each iteration. Okay, that's the most simplest way to do is you just save the BDD in each iteration, and then once you have finished computing it, then you pick a state in the final the fixed point, and then you say, oh, what is what is the next state that you pick a state from there, and then you will have to pick a state in the following thing. Okay, in that such that it is in the original in one of the sets, and the next state is in the BDD in the fixed point. So for example, so this when you save this, what do you have? You have Q0, Q1, Q2, Q3, Q4, etc. up to some Qn when you have reached the fixed point. So I'm assuming that you will save all of them. Okay, and what you'll have to do is you'll have to pick a satisfying instance of a Qn, okay, which is where you will start from, and then you will have to then take its successor, which belongs to Qn minus 1, okay, and so on and so on and so forth, okay. So because that by definition will have, so that will produce the witness, okay, for an EF1 UF2. So pretty much all you have to do is you will have to save those things. And then there is this extra effort of taking a satisfying instance for each of the, so Qn, and then you will have to get a state that goes from that state, okay, into Qn minus 1. Once you've picked Qn minus 1, you do the same thing for Qn minus 1 to Qn minus 2. So your whatever state that you picked from Qn minus 1, so you look for the successor, okay, such that it goes into the next state, okay, and that's what that's what you do. So by just saving the BDDs, you can and then doing a post processing of picking state from each of those things such that they are chained together. So they, then you will accomplish that. So here, the same thing. You will have to save all the things, and you will go from yeah. So it's pretty much the same thing here, except that here you will have one additional additional things. Okay. So let me get that. So where did I? So what you will do is, when you reach a fixed point, what you have is this, okay? If you have saved all of these things, that these are the partial fixed points. Each circle here gives you a partial fixed point. That is, if you're assuming you have saved it there, then what you have to do is, so this chain, it's easy to construct, okay? So you will, will pick one state from this is the fixed point that you generate. From there, you have to pick you have to pick another state which in the previous that you had in the BDD that you had in the previous iteration, and you pick a state from here, and then you apply EX. Okay, so that will give you another state. Okay, satisfying that. So you'll have to get a state from here that is whose successor is in this state, and so on. So you can generate this part, this tail, using that. The only thing is that for EG, you will have to now generate a loop inside this. Once you have a state in here, what you'll have to do is you'll have to do an additional step of generating a witness to this formula EU of F of T, okay? So all you have to do is, so you will have to finally, once you generate the tail, the prefix tail, you have to check this, formula of F. So once you have generated, say, you have generated a T here, okay? You generated a T. So now you know how to generate this tail, okay? Once you have saved all these BDDs, you know how to generate the tail. Now what you have to do is you have to generate this loop, okay? And that's the one that I'm describing, for which you will have to do this F U until T, okay? You have to do, you are in a state T, and you have to do you have to run this, for which you already have. Starting with a T, which is part of this, you already have a state that you have generated here. Now you have to generate that lasso part of the witness, and for which you will have to use this. So you will have to say, from T, I'll have to get back, I have to generate a path in which every path satisfies F1, okay, until I get back, F, until I get back to this will be until I reach T. So I'm starting with a T here, and then I'm going through a path, a loop, along which F continuously holds until I reach a T. So you'll have to do the same witness generating thing, for this. Yeah. Now I do understand this one will require some amount of work. So let's taking Kapil's thing into account. I will I will split it into three parts. One is the basic CTL model checker, okay, and then extending it to fairness. And depending upon how you guys are doing, I will let's take a call to whether to include the third part or not. Okay, so I will do modify it in that way, and depending upon how you guys are doing, I will take a call. Is that fair? Hello? Any feedback?
Yes, sir.
Okay. Yeah. So the key takeaway here is, two things. One is for implementing model checking under fairness, you will have a fixed point computation, another fixed point computation inside the this loop itself. That is one. Okay. Number two.
So you'll be giving the test cases, right?
Yeah. I'll be giving the test cases. Okay. But what I want to do is, in order to help you do this, I don't even mind spending, once a week, some review of your code, and then devoting some time for any issue that you might have, okay, with these two things. But I want you guys to be making progress so that we will discuss any issue that you might have, and in terms of implementation and so on. Yes, we will make up the test cases, for you to test on. Yeah. Okay. So any other comment, Diganta, Rishikesh?
So I think, this might be slightly unrelated, but
What?
so I had a few things, like over here, the main complexity of our thing will be in the elimination of variables in the existential thing, right? As in, that is where potentially the
Correct.
like any exponential factor in complexity may come in, right?
Yeah, but that too only if the intermediate function, every iteration is computing the new Boolean function, correct? So if any one of them Boolean function is such that it cannot be represented, the existential quantification elimination itself is still
Yeah, that
linear, linear in the size, linear time in the size of the BDD. Okay.
right.
So the explosion that you will get will be in if the function result of doing that function is not representable, is representable only with exponential blow up in this in the in terms as a function of the number of variables. Okay.
Right, but then
you will notice it. Okay, so you will not be able to construct in the that will be noticed because you'll have to get the BDD itself, nah? So although strictly speaking it is only linear, but the result output BDD itself can be exponential because the Boolean function that you get is not for that variable ordering only requires an exponential is of exponential size. Okay, so then that is the optimizations that state-of-the-art model checkers will do. They will do, yeah. So that is the complexity that you will get. Okay,
right, so there will be an explosion in the size of the BDD itself.
the size of the BDD, which will be reflected in while constructing the thing. And that's
Right.
why all the
Yeah.
effort of
Yeah, the main.
the transition relation was to avoid that. Okay,
Right.
so that you will be using those tricks, and we're not even getting there. So here, as long as it works, I mean, if it explodes, if the example that we give it explodes, for the small examples for up to 10 things, etc. Even there, it might explode. So unless you do clever things like changing the variable ordering on the fly, the reason for explosion can be because you need a new variable ordering. Okay. Now there are, BDD allows you to do variable, dynamic variable ordering. Okay, you can say, oh, keep changing. You choose your variable ordering. That is one way to avoid it. It uses certain heuristics on the fly to change its variable ordering. Okay, although you might have chosen something in the beginning. Okay. That is one thing. Hey, Zubin, are you still there?
Yeah.
Yeah. What was the, how did you guys did it? Okay. So what is there an option to choose variable, dynamic ordering, and then it'll let it choose?
Yeah, you can let it do that, but by default it's the ordering in which you define variables.
Yeah.
Like the ith, where you give an index to the variables,
Right.
but
So I haven't
then you
just
can
used
turn
that.
on dynamic
You could try that. I mean, since
order.
you brought that thing up, I'm not going to have you, look at optimization, etc. Okay, but that is an option you have. I mean, what can happen very well is if you choose your own ordering right in the beginning, for that particular ordering, the intermediate representation for the intermediate BDDs that you generate before you reach your fixed point can explode. Okay, that'll appear in the fact that you will not be able to, your loop will not will take forever. Okay, because that construction will be the thing. And one optimization is you can use the dynamic variable ordering. Now I don't know how effective that thing is, but that is certainly possible where you don't choose, you let the package choose your variable ordering. Okay, and it can change on the fly, or you will have to do these kinds of partitioning of the transition relation and so on. Yeah. Yeah, I think that with generating the counter example, there's certainly more bookkeeping that you will have to do. Okay, so well, let's see, how you guys are doing. So I'm going to, today is Wednesday, so I think today's Tuesday, Thursday. Next Thursday is when I have it as the extended deadline. I don't know what deadline that I have. Have when you